Okay, so this is the last topic of Chapter 5, and in this topic we'll talk about the substitution rule for definite integration. And this is probably the most, well, again, it's all been very important. This particular topic will be used almost exclusively in your work in calculus too, so pay particular attention to this. It's not that difficult. The substitution rule will be a method we'll use to evaluate particular types of integrals where the antiderivatives aren't too apparent. Okay, it's not too obvious what the antiderivatives of the integrals will be. So, due to the fundamental theorem of calculus, it's important to be able to find antiderivatives. So that's oftentimes the challenge in solving these problems. So, for instance, if we consider this problem, how do we find the antiderivative of this product of two functions? So our anti-differentiation formulas from section 4.9 don't tell us how to calculate the antiderivative of this. Okay, so what do? So to find this integral, we use the problem-solving strategy of introducing something extra. It's a new variable, so we change the variable x to a new variable u. All right. Suppose we let u be the quantity under the root sign in equation 1. So in this case, the integral was this. The indefinite integral was 2x times the square root of 1 plus x squared, differential x, okay? So now if we let u equal to 1 plus x squared, then of course du over dx is 2x dx, or 2x, right? So differential u, recall from chapter 3, is 2x dx. And of course 2x dx appears in our definite integral. So we can reformulate this indefinite integral in terms of the square root of u using a composition times, well, 2x dx is just du. And of course this is something we can handle. This is merely the indefinite integral of u to the 1/2 du, and so we can anti-differentiate that without any issues. That would be u to the 3/2 over 3/2 plus your integration constant. And then you just replace u with its definition in x. So we know that u is equal to 1 plus x squared, so we would have 1 plus x squared raised to the 3/2 times 2/3 plus your integration constant. So this is what we mean by the substitution rule. We come up with a clever way of substituting a known function for the given function so that we can take the antiderivative. All right. So next slides will show you, we'll walk you through this process. So differential x in the notation for the integral were to be interpreted as a differential. Okay, yeah, so chapter 3 stuff. All right. So there it is. There's your answer, just like we stated. Okay, you can walk through that. And then, of course, we can verify that this, in fact, is the answer by taking the derivative. So we'll use the power rule for differentiation, followed by the chain rule. So taking the derivative, we have 3/2 times 2/3 times x squared plus 1 to the 1/2 times 2x. That's the chain rule. And so constants, coefficients will cancel. We'll have x squared plus 1 to the 1/2 times 2x, which we get back our integrand. Pretty neat stuff. Okay. So in general, this method works whenever we have an integral that we can write in the form f composed with g times g prime of x. All right. So it basically has to take the form of a composition. And so here it is, because we're basically using the chain rule in reverse. Okay, so best done with examples. And so the change of variable, we replace g of x with u, and then and so we get a definite integral in terms of u and so forth. So theoretic stuff. So we can write the composition of the integral of a composition of functions as just an integral of a function, and so that's the substitution rule. Okay, so I'll spare you so much most of the theory, it's probably best if we just work through some examples. Okay. So, for instance, consider this equation. So, if we let u equal to the argument of the cosine function, okay, so if we replace this with u, then of course du, taking the differentials of both sides, du is equal to 4x cubed dx. Okay, but we don't have a 4x cubed dx. So what we have to do is we have to say du over 4 is equal to x cubed differential x. Right. All right. So then we'll reformulate the problem. Becomes in terms of u, this would be the indefinite integral of cosine of u times du over 4, which of course is just equal to 1/4 the sine of u plus c. And then you replace u with evaluated at u equals to x squared. I'm sorry, x to the 4th plus 2, like so. Okay. All right. So sometimes you have to apply some algebra to your differentials. So that's shown on the next slide. So yeah, here we go. Okay. All right. All right. So yeah, so the main challenge in using the substitution rule is to find an appropriate substitution. So oftentimes you'll have to do a trial and error approach with your substitution. You may try one substitution and it doesn't work, so you'll have to try an alternative substitution. So there's a little bit of trial and error involved. So it is a bit of an art. There's no theory which tells you. So for instance, if we want to evaluate this this indefinite integral, the suggestion is let u equal 2x plus 1, and then du is equal to 2 dx. So differential x is du over 2, and so what you do then is you'll end up evaluating the square root of u du over 2, which is u to the 3/2 over 3/2 times 1/2. Okay, and so that would be 4/3. Let's see, no, I'm sorry, not 4/3. That would be 1/3 u to the 3/2. Forgot my integration constant. Okay, and so that would be 1/3 2x plus 1. 2x plus 1 to the 1/2 plus your integration constant, like so. Okay, so now you can integrate composite functions. So here's the development. 1/3. Okay, and then you can of course check by taking the derivative of your result. All right. Oh, okay. So they try to, in this case, they try to make d differential u. I would not suggest doing that. This would involve a lot of work. So you have alternatives for your differential u. Okay. Okay. So now how about the evaluation of this one? So they suggest letting u equal to 1 minus 4x squared. Then the differential of u would be negative 8x dx. So x dx is equal to negative 1/8 du. So then you make the substitutions. Okay, replace radical with exponential form. Take the antiderivative. You'll get this result of the antiderivative, which is negative 1/4 times the square root of u, and then you replace u with its definition in x, and so you get this result. So pretty neat stuff. All right. So they want to check the answer graphically. So here we've used a computer to graph x over, okay, so I guess that was it. And it's indefinite integral. All right, in this case we take c equal to 0. So what are they trying to shoot for here? Oh, okay, so g of x decreases when f of x is negative, yeah, and increases when f of x is positive, sure, and it has a minimum when f of x is 0. Okay, yeah. Well, that kind of gives you a guidance, okay? All right. Okay. Calculate e to the 5x. So if we let u equal 5x, then du is equal to 5 dx. So dx is equal to 1/5 du. So replacing the function 5x with u, take the antiderivative of e to the u, which is e to the u. So it's 1/5 e to the u plus your integration constant, and then plug back in u. So no challenge there. Okay, so, oh, now here's a challenging one. All right, so find the indefinite integral of the square root of 1 plus x squared times x to the 5th. So as appropriate substitute, so if we factor x to the 5th as x to the 4th times x. All right, so yeah, so if we let u equal to 1 plus x squared, then du is equal to 2x dx. So x dx is equal to du over 2. So we're left with something like this. The square root of u, and then x to the 4th times x. Dx like this, okay? Now x dx is du over 2. So then we have x dx is du over 2. So now we need to replace x to the 4th in terms of u. All right, so we know that, so here's how we can do it. We know that u is equal to 1 plus x squared. Okay, now what is x to the 4th in terms of u? So u minus 1 is equal to x squared. So we have, so I'll continue here. So we've got this. So we have the square root of u times x to the 4th times du over 2. So u is equal to 1 plus x squared. So u minus 1 is equal to x squared. So if we square both sides, we'll have u minus 1 quantity squared is equal to x to the 4th. All right, so now we can replace that in our indefinite integral. So we have the square root of u times u minus 1 squared times du over 2. All right, so remember, so we can evaluate this indefinite integral now. Just go ahead and replace the radical with its exponential form and expand the square, the binomial square, so that would be u squared plus 2u plus 1 times du, and we can kick the half out. And just go ahead and do the multiplication inside the integral operator. So this is equal to 1/2 times u to the 3 halves. I'm sorry, 5 halves, right? 5 halves. 1/2 plus 2 is 5 halves. So the u to the 5 halves plus 2u to the 3 halves plus u to the 1/2. Okay, and then we just go term by term, taking the antiderivative of each term. All right, so this would be 1/2 times u to the, what, add 1? So that would be u to the 7 halves over 7 halves plus 2 times u to the 5 halves over 5 halves plus u to the 3 halves over 3 halves. Okay, like so, plus your integration constant. So this would be 7u to the 3 halves, no, 1/7. 1/7 u to the 3 halves plus u to 1/5 u to the 5 halves plus 1/3 u to the 3 halves plus c, and then of course we evaluate this at u is equal to what? 1 plus x squared. So we just plug in 1 plus x squared, and then we'll have our answer. All right, so the key to this problem was recognizing that we had to factor x to the 5th. All right, so it was a tricky problem, right? So it involved just a fair amount of algebra, I would say. And so here it is. There it is, stood up for you. X to the 4th is u minus 1 in quantity squared. Okay. Calculate the indefinite integral of tan x. Replace tan x with its definition sine and cosine x. And then if we let u equal to cosine x, then du, of course, is equal to what? Cosine minus sine x dx, right? Minus sine x dx. And so, so sine x dx is equal to the negative of the differential of u. And so we have the negative of the differential of u over u, and so that becomes the antiderivative of 1 over u, of course, is the absolute natural log of the absolute value of u, so we have the negative of the natural log of absolute value plus c, and then replace u with its definition. So this is the antiderivative of tan function. Okay, all right. And since the negative of the natural log of absolute value of cosine x is equal to the natural log of the absolute value of cosine x to the negative 1, which is 1 over cosine. So it's actually the natural log of the absolute value of the secant function. So you can also write the indefinite integral of tan x is equal to the natural log of the absolute value of the secant function plus your integration constant. All right, so we can use the substitution rule for definite integrals as well. Okay, and there are 2 techniques. So let me show you how that's done. So let's consider the definite integral from 0 to 4 of the square root of 2x plus 1. So you can basically evaluate, you basically calculate the indefinite integral, okay, which we did before, and then use the net change theorem. All right, so that's one way. You cast off the bounds of integration, convert it to an indefinite integral problem, solve the indefinite integral problem, and then apply the net change theorem in the final step. Or you can, another method, which is usually preferable, is to change the limits of integration when the variable is changed. So oftentimes that's done. So here's the theoretic result. So for instance, if you replace g of x in this expression with u, okay, and g prime of x dx would be, of course, the differential, then your bounds would be changed by replacing a with g of a and b with g of b. All right, so I find it easier to look at examples than to go through this theoretic step here. So let's see, let's skip to some examples. So evaluate this using the change of change of bounds of the integral. So using the substitution. All right, so we know that if u is equal to 2x plus 1, then du, of course, is du over 2. So what happens is what they're essentially saying is this. The problem transformed in terms of u is like this. Okay, so it becomes the square root of u times du over 2. Now, if x equals 0, what does u equal to? All right, so remember this lower bound is an x value. So if x equals 0, then u is equal to 1. And if x equals to 4, then u is equal to 9. Okay, so the transform problem in terms of u becomes this. So then it would be 1/2 u to the 3 halves over 3 halves. Evaluate it from u equals 1 to 9. Okay, so that's what they're saying. Just replace the bounds, the bounds in x in terms of the bounds of u based on the relationship between u and x. All right, so that's all you have to do for changing the limits of integration. None of this graphing stuff is really necessary. Yeah, and here they go. So yeah, as you can see, they replaced the bounds and then proceeded to evaluate the definite integral. Yeah, and then you never have to return to x. You're just chasing a number. A definite integral is just going to give you a number. All right, so in this case, we can use the substitution rule for definite integrals here. So the integral from 1 to 2 of 1 over 3 minus 5x quantity squared. So if we let u equal 3 minus 5x, then du is equal to minus 5 dx, so dx is equal to minus 5 du. All right, and so now when x is 1, okay, when x is 1 right here, then we plug the 1 in there to get a lower bound in u, so u is minus 2. And when x is 2, then u is minus 7. So the transformed integral will go from minus 2 to minus 7 of 1 over u squared. And what is dx? dx is minus du over 5. Okay, now, and then of course we can negate this, so this would actually be, if we changed the limits of integration, if we flipped them, we would have to negate the integral, so this negative sign would go away. So it would be from negative 7 to negative 2, 1/5 du, such like that. Okay, so that's how we can evaluate that. All right, so that'll be shown in the next slides. So here they go, they replace, and then surprisingly they didn't change. They decided not to flip the bounds of integration. They just left it there, which is fine. And so you evaluate 1 over 5u from, why did they? I think this should be negative 2. Oops. I think this is a typo here. I think this should be negative 2 right there, not negative 5. Okay, and so the answer is 1/14. Okay. Okay, so calculate the indefinite integral, or the definite integral now, of natural log x over x from 1 to e. So we let u equal to ln x, then du, of course, is dx over x. So, and then when x is 1, okay, u is equal to the natural log of 1, which is 0. And when x is e, u is equal to the natural log of e, which is 1. So we can transform the problem into a very simple problem. The definite integral from 0 to 1 of u du, which is u squared over 2 from 0 to 1, which is a half. So this is equal to a half. Okay. Yeah, so the integral represents the area under the curve from 1 to e of ln x over x. So there you have it. Symmetry. Okay, so the substitution rule for definite integrals to simplify calculations of integrals of functions that possess symmetry. So this is particularly an intriguing section. Suppose f is continuous on negative a to 8. So intervals like this are called symmetric intervals. Okay, they're symmetric with respect to the origin of the coordinate plane. So these are called symmetric intervals. And if you have a continuous function on a symmetric interval, and if that function is even, then you can even reduce further the amount of work you do by replacing the bounds of integration from 0 to a and then doubling the result. If it's odd, this is particularly nice, the definite integral of an odd function over a symmetric interval is 0. Okay, so that's very nice. We like to see a lot of those. Okay, it involves no computation. So here's the reason. We can split the integral in 2 pieces at 0, and then we can and then you can format it this way if you wish. Okay. So we have, so here we go. So they make okay. So if, for instance, if this f of x were an even function, the first integral and the second part, we can make the substitution u equals negative x, and du is equal to negative. Okay, yeah. So yeah, okay. So all they're showing then for an even function, the negative of the definite integral from 0 to minus a is the negative. So if you flip the to flip the bounds. Okay. Yeah, so I think you can trace through that using the properties of the integrals. So let's keep going. Let's jump to the result here for even functions. So they prove it for even functions, and I guess they'll prove it for odd functions as well. The only thing we need out of here is just the result. All right, so for instance, here's a chart showing, or a graph showing the area under the curve of an even function on a symmetric interval. You can see that it's just twice the golden area. The area under the curve of an odd function on a symmetric interval, the areas will cancel. That's the result that we really need to know. Okay, so maybe we can find some examples here instead of all this theoretic stuff. All right, 62. Slide 63, I'm looking for some examples. Okay, so yeah, here's a good example. So consider x to the 6 plus 1, which is an even function. And so we want to find the area under the curve of x to the 6 plus 1 from -2 to 2. So the rule says that we can, since the interval of integration is symmetric, we can replace the lower bound of the definite integral with 0 and then double the result of the transformed integral. And so all you have to do is evaluate this this integral. So take the antiderivative, so it would be x to the 7 over 7 plus x. Use net change, evaluate it from 0 to 2, and then so you'll have 128 over 7 plus 2. The 0 is nice because now we just plug in 0 for x, nothing to do there. And then we double the result, and it's 284 over 7. So symmetric functions, okay? And then I think the last case will be an odd function. So yeah, so consider tan x over 1 plus x squared plus x to the 4th. So clearly, tan is an odd function. An odd function over an even function is an odd function. And so if we integrate this odd function over a symmetric interval, then of course the result is 0. So no need to compute an antiderivative here. All right, so this concludes Chapter 5. And so now, and pretty much the technical matters for the class. So come to class. In our next class, or if we have time today, we need to talk about a potential test on Chapter 5. And of course, a lot of this material will roll into the final exam, which is going to be heavily laden with Chapter 5 concepts. So these notes will be discussed. These topics will be discussed in class. Also, you need to have all of your web assignments for the semester nearing completion, as well as your Chapter 5 project. So as usual, you can email me for hints, see me during my office hour, and then attend class so that we can discuss the parameters of the final exam. All right, so this concludes the lecture content for the class as well as for the course.